Being asked which of the following is the source, the oligodendrocytes, which myelinate the optic nerve. So we're giving this information in the passage. What you have to know is that the oligodendrocytes function similar to Schwann cells in the peripheral nervous system, except that the oligodendrocytes will myelinate the axons for the central nervous system. And again, glial cells are going to be non-neuronal cells which help to maintain the function and structure of neurons. With the peripheral nervous system, you have the Schwann cells, which myelinate axons, and in the central nervous system, you have oligodendrocytes. And so the answer is going to be D for question number 1. For question 2, you're being asked which of the following is most similar in reference to glial cells that are oligodendrocytes, in reference to where they appear in the subdivisions of the nervous system. Notice that oligodendrocytes are going to be in the central nervous system, as mentioned earlier, as well as astrocytes and microglial cells, or microglia, which are in essence macrophages or macrophage, however you want to pronounce it, in reference to immune function. And astrocytes are going to help maintain the structure of epithelial tight junctions that maintain the blood-brain barrier in the central nervous system. Which of the following options best summarizes the clinical use or the function of the clinical use of atropine as described in the passage? So although A is correct and plausible as an answer choice, you don't just want to look for whichever answer choice is stating something that is true. You want to make sure that you select something that answers the question. And so if we look through the answer choices, B is factually incorrect due to the fact that atropine will inhibit the action of acetylcholine in reference to its parasympathetic stimulation on the muscarinic cholinergic receptors of the eye, which function to constrict in the stimulation of light. And so it constricts the pupil, which reduces the amount of light entering the eye. And this is a protective function to reduce the amount of light that is transmitted to the retina. But because atropine is going to have the inhibitory effect on acetylcholine, we cannot say that it's going to mimic it. Furthermore, in the same answer, it says that acetylcholine functions similar to epinephrine, which is secreted from the adrenal cortex. This is incorrect. Acetylcholine is not going to have similar effects to epinephrine, and epinephrine is secreted from the adrenal medulla, not the adrenal cortex. The adrenal cortex secretes cortisone or hydrocortisone in reference to the stress response or prolonged stress response. Now, acetylcholine does a few different things. It could be excitatory and or inhibitory, but in reference to the passage, it has parasympathetic properties in reference to its stimulation on the muscarinic receptors of the eye in reference to the muscles, which constrict the pupil, which is to say that B is incorrect. C says that, what does C say? Okay. It says that it's a beta adrenergic antagonist. This would be incorrect. If anything, it would be a beta adrenergic agonist, but that's not correct either. But due to the fact that it inhibits parasympathetic stimulation, it's going to be a sympathetic agonist. And so keep in mind that in the passage it says that the beta adrenergic stimulation enables the pupil to remain dilated. And so if anything, it would be a beta adrenergic agonist in allowing the pupil to be dilated. But the more proper response is in answer choice D. And again, C we can cross out due to the fact that it says it's a beta adrenergic antagonist. So that's the one word that we can eliminate answer choice C with. Now with answer choice D, it summarizes the effect of atropine on acetylcholine in reference to inhibiting its parasympathetic muscarinic cholinergic stimulation on the pupil, which otherwise functions to reduce the diameter of the pupil. And so D is the best answer. With question number 4, you're being asked what is the correct stereogenic classification of the chiral center in molecule 3. So whenever you have a chiral center with 3 or 4 of the same atoms, you want to move on to the next one, and you give priority to whichever substituent has the atoms of highest molecular weight, which is to say that the carbonyl carbon takes priority over the carbon pertaining to the alcohol. And this is due to the fact that the carbonyl carbon of an ester is in essence bonded to 3 oxygens, which takes precedence over a carbon which is bonded to 1 oxygen. And so following the direction, notice that you have 1, 2, 3 in clockwise fashion, which is to say that it should be R. However, the lowest group, which is the hydrogen, remember, see the invisible, draw the invisible, is going to be facing you due to the fact that the substituent leading to the alcohol is going to be dashed. And so that means we invert the configuration, giving it an S for the chiral center. For question 5, you're being asked in reference to physics, in reference to some of the potential side effects of atropine and medications similar to it, as provided in molecules 1, 2, 3, and 4. What's important to note is that if it has the potential to inhibit the accommodative function of the eye in reference to being able to focus objects at close distance when it comes to, let's say, reading something, if that function is inhibited, then what's going to happen is the eye is not going to be able to converge the image directly on the retina. And so as a result, it will converge behind the retina, which gives for a blurry image. And so this would be most closely resembling issues with hyperopia, where the person can see objects far away, but objects in close distance are not able to focus soon enough, and so they converge behind the retina, giving a blurry image, which is why you want to have convex lenses, corrective lenses for these type of situations, at least with basic, very, very basic eye correction, or I should say corrective lenses, right? There's a lot more to it, but in reference to the fundamentals that you have to know for the MCAT and the OAT, if a person is, or if a person has hyperopia, the image converges behind the retina, and so we have to have corrective lenses that enable the converging power of the image to increase so that it focuses a little bit more sooner on the retina. In contrast, people with myopia have it so that they converge the image a little bit too soon, just in front of the retina, and so as a result, you want to have diverging or biconcave lenses so that they enable the conversion of the image a little bit later. And so we're reducing the converging power of the eye, or the lens, right? So that the image lands directly on the retina, which gives for a clear image. So all that to say that the best answer is going to be D in reference to the potential side effects of accommodation being diminished with patients that have pupils dilated for an extended period of time. This would most closely reflect patients with hyperopia. With question number 6, we're looking at which of the following reagents would best distinguish between molecules 1 and 3. Notice that there's a lot of different functional groups, but commonalities and what we want to focus our attention to would be the alcohols and the carbonyl groups. Notice that all of their reagents are oxidative or reductive reagents. And one fundamental principle that you have to know about oxidation is not the mechanism, but if you have a tertiary alcohol, you will not be able to oxidize it. Which is to say, in comparing a compound with a tertiary alcohol and a primary alcohol, if we use pyridium chlorochromate, we're going to be able to oxidize only the primary alcohol. Which is to say that if we compare the spectral data in reference to IR spectra, only one of them is going to have the disappearance of the broad absorption of the OH stretch, characteristic of hydroxyl groups, around the 3500 region. Which is to say that PCC would be the best reagent to distinguish between molecules 1 and 3, in that it would only react with molecule 3. Now, sodium borohydride doesn't react with either of those compounds, so that's not useful. And lithium aluminum hydride reacts with both of the compounds due to the fact that both of the carbonyls are esters. But if we have IR spectra that are going to be similar, then that's not going to be useful to distinguish between the two compounds. Now, if you use a more potent oxidative agent, such as Cr2O7, you have only one of the molecules reacting with that. However, the IR spectra is going to look similar to molecule 1. Why? Due to the fact that if you have a primary alcohol and a strong oxidative reagent, that's going to lead that's going to lead to a carboxylic acid, which means that you're still going to have an OH stretch, and as a result, not be able to determine which is which, just from looking at the IR. And so again, the best answer is going to be pyridium chlorochromate, due to the fact that molecule 3 will have the disappearance of the OH stretch, characteristic of hydroxyls around the 3500 region. The next question is asking very simply what is going to be the number of sp2 hybridized atoms in the molecule. And the key thing to remember here is to, yes, see the invisible, draw the invisible in reference to the lone pair on the nitrogen for the amide group. And so it may appear to be an sp3 hybridized atom, but all nitrogens of amide groups are actually sp2 hybridized due to the fact that it has better ability to have resonance with the carbonyl oxygen. And so although it does have 4 electron densities with 3 sigma bonds and 1 lone pair, the nitrogen pertaining to amides will always be sp2 hybridized. Last question, which of the following is going to give an aldehyde and a ketone based on the series of reagents below? So in a multi-step synthesis, you're being asked which one gives you the aldehyde and the ketone. So first of all, notice that if you have a oxidative reagent with a secondary alcohol or a very weak oxidative reagent with a secondary alcohol, the result is going to be the same nonetheless. You're going to have a ketone due to the fact that the number of times that you can oxidize an alcohol is going to be determined by the number of hydrogens that carbon bonded to the hydroxyl has. And so a secondary alcohol has 1 hydrogen. Therefore, you could only oxidize it 1 time. And so if we follow this with the ethylene glycol, or the OHCH2CH2OH in hydrochloric acid, this gives for the formation of an acetyl group, which functions to protect aldehydes and ketones. So the recently oxidized secondary alcohol, which gives you the ketone, is now protected through the acetyl group, and the subsequent step, which is Dbol H, a selective reductant, which reduces all carbonyl compounds and converts them into aldehydes. So whether it's a carboxylic acid, a malonic ester, or an anhydride, or in this case an ester, the result is going to be the same. You're going to establish a sigma bond to a hydrogen in place of the sigma bond to the oxygen group. Whether it's a carboxylic acid or an ester, the result is going to be the conversion of the ester to the aldehyde. Notice that the workup step is H+, which enables the reformation of the ketone. And so the answer is going to be the molecule containing the secondary alcohol,